So welcome to our kind of next new lesson in our organic chemistry exploration here. And the title of today's lesson is called Assigning Formal Charge. And so our learning target for the lesson is to be able to assign what's called a formal charge to any atom within a molecule. And so the last lesson that we had done before kind of school let out is a lesson that was called conjugation. And if you remember, what happened there is we had different molecules that had kind of a system of alternating double bonds. Now, due to those double bonds, each of the atoms kind of within that system had a p orbital. And what we could do is we could take the electrons and kind of spread them over the molecule, so to say. All right, so it created kind of one big system of spread out electrons instead of the electrons being assigned to just one atom. Okay, so now what we're going to do is kind of take a step back and look at the electrons from kind of a one atom perspective, as in how many electrons does an atom tend to, quote, own within a molecule. And what you'll notice on these notes is a little different, is I've done a little more kind of typing out. I know for some of you guys, you may not be able to or may not want to, print these out. And that way, if you choose to save them, and take them on with you to college sometime and use them later, that way you've got more of the text, with you. That way you can remember, what we might have said in class. So I'll just kind of read this first part and then we'll get on with some practice. So it says atoms within a molecule can take on different charges depending on the presence or absence of electrons in that region of the molecule. And so to decide if an atom itself is positive, negative, or neutral, we need to assign a formal charge. And so what formal charge is it's the difference between the valence or outer electrons of an atom and how many electrons it owns in that particular Lewis structure. And so get a reminder here, remember that the way you find valence electrons is by looking at the atom's group number. So things in group 1 have 1 valence electron, things in group 2 have 2 valence electrons, so on and so forth, all the way from groups 13 to 18. Okay. And so the definition, when you first read that, you're kind of like, what? So let's see if we can take a look at an example and kind of put those words into meaning. So the way you go about calculating the formal charge is you first kind of note the valence electrons that atom has. So here, our atom in question is nitrogen, all right? So if we looked on our periodic table, we would find nitrogen in group 15, or in other words, group 5A. So it means that nitrogen would have 5 valence electrons, all right? So this is your valence electrons. Then what we subtract is the number of electrons that are owned within the molecule. So 5 electrons, the valence electrons, is what nitrogen brings to the table. And then we're going to take away how many he still has in the molecule. And the way you figure that out is by adding up the non-bonding lone pairs plus the number of bonds. That's kind of this little formula here. So the non-bonding electrons, aka the lone pairs, plus the number of bonds. So here I have 4 electrons in lone pairs plus 2 bonds, all right? So that gets me a total of 6 electrons that it's owning within the molecule. 5 minus 6 is a -1 charge. So that means nitrogen kind of owns 1 more electron than what it brought into the molecule to start with. And so that's what will give it kind of a formal charge of -1. And the way we note formal charges are with these little kind of symbols, either a minus sign for a negative formal charge, a positive sign for a positive formal charge, or if it's neutral, we just write nothing. Okay. And so if you look at molecules kind of enough, there are some general kind of formal charge patterns that you begin to see. So for example, some of our common organic chem elements, like carbon, typically when carbon has 4 bonds, it has a formal charge of 0. That's because it starts with 4 valence electrons minus 4 bonds equals 0. If you see carbon with a 1 lone pair, it typically has a negative charge of 1. That's because 4 valence electrons minus 1, 2, 3, 4, 5 electrons from the molecule gives you negative 1. And then if you see carbon with 3 bonds and no lone pair, that typically gives you a positive 1 formal charge because 4 valence electrons minus 1, 2, 3 electrons from the bonds gives you a positive 1. Okay, and you'll kind of start to pick up on these patterns the more you see them. So typically carbon with 4 bonds is neutral. Typically for nitrogen, nitrogen likes to have 3 bonds and 1 lone pair to be neutral. For oxygen, typically 2 lone pairs and 2 bonds is neutral, while 1 bond and 3 lone pairs is a negative formal charge. That'll be common. And then for chlorine, chlorine prefers to have 1 bond and kind of 3 lone pairs, and that goes for the other halogens as well, group 17. And then hydrogen, of course, to be neutral, likes to have just 1 bond. Okay. And so as we go forward, kind of some general guidelines is typically most things like a minimized formal charge. They would prefer to be neutral, okay? But, however, if you do have atoms that are charged, you want to put the positive charge on the least electronegative atom, and you want to put the negative charge on the most electronegative atom because it will be better able to stabilize or attract it, okay? And then the sum of the formal charges on the atoms must add up to equal the overall charge on the molecule. So let's go through and kind of do some examples here. So the instructions might say, assign formal charges to the atoms within the molecule. All right, and so we're going to try to build some patterns kind of as we go through these. So here, let's go ahead and start off with hydrogen. I know hydrogen is in group 1, so it has 1 valence electron, and it has 1 bond. So 1 minus 1 gets me 0. And if we remember that's a pattern, hydrogen with just 1 bond has a 0 formal charge. So that'll be the case for both of these hydrogens. Since they have a 0 formal charge, we won't write anything. All right, now let's take a look at this carbon. Carbon has 4 valence electrons. So let's go ahead and count around. 1, 2, 3, 4. So 4 minus 4 is 0. So again, carbon with 4 bonds has a neutral formal charge. Now let's look at this nitrogen in the center. Nitrogen is in group 15. It has 5 valence electrons. Let's count around. 1, 2, 3, 4. 4 bonds, no lone pairs. 5 minus 4 is positive 1. So, we get to assign our first formal charge there. So we'll put a little plus sign and a circle there for nitrogen. Now let's take care of the nitrogen on the end. So nitrogen again starts with 5 valence electrons. Let's count around. 1, 2, 3, 4, 5, 6. 5 minus 6 gets us negative 1 for this nitrogen. So we'll put a negative in a circle. And it works out because overall the molecule is neutral. So positive 1 plus negative 1 equals 0. All right. So now let's go ahead and try B. So the CH3, if you'll kind of visualize it with me, that's just where you have a carbon attached to 3 hydrogens. And so each hydrogen has 1 bond. Carbon has 4 bonds. So we know that pattern should mean that each of those atoms have a 0 or a neutral formal charge. So we're good to move on. So let's take a look at our oxygen. Oxygen starts out with 6 valence electrons. So let's count around. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. And again, that's another one of our patterns that oxygen, when it is double bonded or has 2 bonds and 2 lone pairs, should have a neutral formal charge. All right, so let's go back and tackle that next atom. So next we have nitrogen. Nitrogen is in group 15, 5 valence electrons. Then we count around. 1, 2, 3, 4, 5. 5 minus 5 is 0, so it's neutral there. And then finally, let's take a look at this oxygen at the end. Oxygen has 6 valence electrons. Let's count around and subtract. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So nice. So this molecule has a really stable structure. Everything tends to have a neutral formal charge. All right. So just 2 more here right quick. So we've got carbon, or 3 more rather. Sorry, couldn't count there. So here we have carbon that does not have 4 bonds. So we can probably expect it's going to have some type of formal charge. Carbon starts with 4 valence electrons, then let's count around. 1, 2, 3, 4, 5. 4 minus 5 is -1, so we'll assign him a negative formal charge. Let's take a look at oxygen. So oxygen typically brings 6 valence electrons. Let's count around. 1, 2, 3, 4, 5. 6 minus 5 is also +1. So he'll have a positive formal charge. Those formal charges balance out to give us an overall neutral molecule. All right, moving on to our last 2 examples. So hydrogen, we can tell, has 1 bond, so he should be good to go. No formal charge. Carbon has 4 bonds, no formal charge there. Nitrogen isn't following his 3 bond, 1 lone pair pattern, so he's probably going to have a formal charge. Nitrogen starts with 5 valence electrons, and let's count around. 1, 2, 3, 4. 5 minus 4 is +1. Then we have oxygen on the right-hand side here. Let's go ahead and do him. Oxygen typically starts with 6 valence electrons. 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals -1. So he'll have a negative formal charge. And again, that's another pattern that when oxygen has 1 bond and 3 lone pairs, it's typically negative. All right, and last but not least, this actually is ozone right here, O3. So let's see if we can assign some formal charges to its atoms. So this oxygen here has a double bond and 2 lone pairs. So if we're thinking 2 bonds, 2 lone pairs, just based on pattern, that should be neutral. All right, let's go ahead and do our middle atom. It's not following the neutral kind of pattern, so we should need to calculate its formal charge. Oxygen starts with 6 valence electrons, then we'll count around. 1, 2, 3, 4, 5. 6 minus 5 is +1. It gets a positive formal charge. And then finally, let's tackle that last oxygen. If we remember from the previous molecule that an oxygen with 1 bond and 3 lone pairs is -1, we can verify that just to be sure. Oxygen starts with 6 valence electrons. Let's count around. 1, 2, 3, 4, 5, 6, 7. But it possesses 7 in the molecule. So that's where the -1 charge comes from. All right. So now let's kind of flip to the back and give you a chance to practice on your own. So it says, given the structures below, assign any missing formal charges. So go ahead right quick and pause the video, give these a try, and then when you're ready to check your answer, go ahead and restart the video and the answers will appear. And so again, kind of just try this first part first. All right, so here we are kind of back with the answers. And it's interesting because these are all structures of kind of the polyatomic ions that we're familiar with from our blue reference sheet. And so what's interesting is if we kind of take a look at the formal charges, they kind of help explain why the polyatomic ions carry the charge that they do. For example, sulfate as an ion has an overall -2 charge. And if we look at its formal charges, that sulfur in the middle has a +2 charge, and then each of the oxygens have a -1 charge. -4 plus +2 gives you an overall -2 charge. And so it's just kind of interesting that that's where those ion charges come from, is combining the formal charges of your atom. All right, so take a moment, kind of check and see how you did, and definitely let me know if you have any questions or if one of these doesn't quite make sense. Then what I'd like you to do is, again, kind of pause the video and try the 2 problems on the other side of this line where you're trying to see which Lewis structure better distributes formal charge. And so the idea is, again, most things want their formal charge minimized, meaning that you want to have things that are neutral, okay, instead of having lots of charges over the molecule. If you do have to have a charge, put the negative charges on the more electronegative atoms because they can handle them better. So go ahead and pause the video right quick, try those next two problems, and then we'll pop up the answers in just a sec. All right. So our question was, which structure of each pair better allots formal charge? So in this first example, structure 2 was better because it minimized formal charge. Everything was neutral. But in the first one, sulfur required a positive 2 charge and carbon required a negative 2 charge. And then in the second option there, both were best. And that's because these are just resonant structures of each other. Since we did have to have a formal charge, they put the formal charge on oxygen, which is more electronegative than nitrogen. So both of these did a good job. All right. So now just kind of one more little closing thought before we send you off to practice some more. So I'll read this last part to you. It says, assigning formal charges to specific atoms makes it seem as if the electrons belong to just that individual atom. And we call this localization, all right? So it seems like those electrons are localized on one atom. And so just like when you shop local, your money stays in your hometown, when electrons are, quote, local, they stay with that one atom, all right? And so this is where sometimes formal charge can be a little misleading, because oftentimes, instead of being localized to one atom, electrons are in fact delocalized or spread across multiple atoms within the molecule. This was exactly what was happening when we introduced the concept of conjugation in a previous lesson. And so just to refresh you on that right quick, so in conjugation, 3 or more p orbitals join together into a larger pi system. These pi systems contain pi electrons that are delocalized across any atom that participates in the system. And kind of one famous example of that is benzene, C6H6. And what's interesting is each carbon in this structure is sp2 hybridized, okay? And so it looks like each of those carbons have a neutral formal charge, so that's good. But due to their hybridization, they each have a p orbital that can then spread kind of those pi electrons throughout the molecule, okay? And so instead of the electrons being reserved just for each individual carbon, they can kind of be shared or delocalized throughout the system, okay? And so what happens is instead of having kind of alternating double and single bonds, the real molecule has kind of bond links that are in between those two bonds because the electrons can be shared. And sometimes because of this, you'll see benzene drawn as a hexagon, but instead of drawing in the double bonds and single bonds, they'll just draw in a ring in the center to kind of remind you that those electrons are delocalized throughout the ring. So you don't have technically double bond, single bond, double bond, single bond, but the bonds are all the same and they're kind of somewhere in between those two different electrons. And so this is going to kind of bring us to the need for our next lesson, which is the idea of resonance structures. We've talked about that a little bit before, but we're going to go deeper and show how we can go beyond the formal charge and start representing when electrons are no longer reserved for one atom, but they can be delocalized and better give us a picture of the overall atom, okay? And so just as a reminder, kind of where this delocalization is going to come into play is typically you'll see the delocalization when you have double bonds, all right? And then other times, if you have lone pairs adjacent to double bonds, they'll be able to participate in that delocalization as well. So it's just something to watch out for in the next lesson. So that's kind of our notes portion. And so what we're going to do right quick is I'm going to show you what the practice will look like. And so what the practice is, it's called Formal Charge Interactive Worksheet. And what it is it's kind of the questions that we would have done on the whiteboards in class. But, we're not in class at the moment and can't quite, go around the room and do that. So what we've got is kind of the little practice problems, and there are little charges on the side of the worksheet. And if you'll click on View and Zoom, you can zoom in to where you have a better view of the problems. And so it says identify any formal charge in the following structure. And so what you can do if an atom has a formal charge is you just grab one of the charges and just kind of drag it over to the atom. So if I think this oxygen has a positive formal charge, I just kind of drag the positive, over to him. And if you need more, you can always, copy and paste. There are negative charges on the right, positive charges on the, negative charges on the right, positive charges on the left. And that's how you can kind of use them to complete the worksheet. And then at the end, there will be answers and kind of instructions for how to go about checking yourself. All right, thanks so much for your patience as we went through the notes, and good luck as you practice.